So when thinking about the wave function, we can go back to our double slit interference. So if we put electrons through a double slit, you get an image that looks something like this, where you can see we're getting this strong interference pattern. And if you want to look at it in terms of, obviously not to scale, here's our double slit, right? We have electrons that come towards these. They form these waves. This wave is the de Broglie wavelength, and the electrons are positioned on the detector. This gives us an intensity, and the intensity, it turns out, is something called the wave function squared. Now, this goes back to the idea that the probability of finding something in a certain region is going to be the probability density times this delta x, right? That's just this little space, right? So if you're looking here, that's going to be this value here, okay? So right there. And so we also know that the probability is always related to the amplitude squared, where the wave function, if you take the absolute value and square it, should give you the amplitude squared at that point, okay? So the wave function is a new thing we're introducing, and it's going to give you, if you square it, it's going to give you the probability of finding a particle at a particular point, all right? So let's talk a little bit more about what that means. In classical mechanics, we determine position completely by its function in time, okay? So a particle is completely determined x as a function of time. Now, in quantum mechanics, a particle is described by its wave function instead of just a position, just one value x. Now, the wave function is a little bit different, and the reason we've been talking about statistics is the wave function is sort of a statistical probability of where you're going to find the particle, okay? So here's a wave function. This is along the x-axis, so you can see there's lots of places the particle can be. So the particle can be here, the particle can be here, the particle can be here, the particle can be here. And the reason we have a wave function is we don't exactly know where it is anymore. So in this case, in the classical mechanical case, you would say, okay, if you graphed where your particle was, it would just be a point somewhere on this line. Now that we're using a wave function, we don't know where it is, but we can narrow down the places where it is. So you can see it's probably not at 0, and it's pretty unlikely to be out here, okay? So we narrow down the places where it can be. Now this is a little bit weird when you're thinking about the macroscopic world, because usually when we have an object, we pretty much know where it is. So anyway, a particle is completely described by its wave function. The probability density indicates how likely you are to find something in a particular location. So if you look at the wave function, it's likely to find things at b or negative b. That means the probability density is highest at b and negative b. It also means because it's unlikely to find it at 0 or outside, far away from 0, you can see the probability density goes to 0. So probability density indicates the likelihood of finding a particle at a particular location. And so remember, the thing that we're changing here is in classical mechanics, we always know the location of a particle. In quantum mechanics, we don't know exactly where the particle is, and that gives us the possibility of interference, because that means things can hypothetically be in sort of two places at once in order to interfere with themselves. And I know that's a little bit weird, but consider that this is a range of physics that's far outside of your sort of everyday experience. So let's try this out. So for now, just take for granted that the wave function is a thing. This is the wave function for a neutron, let's say, and at what value of x is the neutron most likely to be found? Okay, so remember, this is the wave function, and if we want to know the probability, we're going to square the wave function, which means everything's going to be positive and the big things will be bigger. So since this is going to be squared, when it's squared, that means we're most likely to find our particle, our neutron, at x sub c, because that's where the square of this function would be the largest. Okay. So let's talk about probability and the wave function. So remember, we are always choosing these sort of narrow bands of width delta x. Delta just means something really, really small, this lowercase delta. So if we want to figure out the probability we're in a particular range, we do it just the way we were doing at the beginning of the chapter, where we just integrate over that range, okay? And when we integrate over that range, we pretty much either get p of x, which is the wave function squared, delta x, or if you want to get a little bit wider range, right, you integrate from one point to another. So this would just be an estimate. It's sort of like when you do the rectangular approximation for an integral, but if you want a really precise answer, then you actually use the integration, okay, and you integrate the function. And the function that gives you the probability is the wave function squared. So for instance, here, if we want to figure out the probability that we're between xl and xr, which would be x to the left and x to the right, we integrate the function from xl to xr, and it should give us some sort of probability like something in the less than 100%. Because what happens if you integrate over the whole thing? Okay, well, if you integrate over the whole thing, the probability of landing somewhere on the wall has to be 1, because we know we're going to detect it if we look all over the wall. So if you integrate from negative infinity to infinity, meaning over the entire function, you should get 1. And this is just the same thing as what we were talking about when we had that target earlier in the previous section, where you had all of these marks on the target, and the probability, when you added up the probability of landing in A, probability of landing in B, and probability of landing in C, had to be 100%, because it has to land somewhere, okay? Now, we use this to actually find some important values, and we'll see this in a minute. This is called the normalization condition. And what this is used for is that you need to normalize your wave function so that whenever you do these integrals, all of your possible outcomes add up to get 1, because we know that has to be true based on how probability works. So for a wave of light, it's very clear what the amplitude is, and the amplitude is the maximum oscillation of the electromagnetic field. So when we have to make it correspond to a statistical value. So we have to know what 100% means by integrating over the whole function, and then anything else is going to be some fraction of that. So we call this the normalization condition, and once we find a wave function, we often have to normalize it so that when we do integrate to get probability, we get a probability that makes sense. So here's an example that we'll do. This figure shows the wave function of a particular particle confined within the region of 0 and L, okay, where L is 1 nanometer. We know the wave function is 0 outside this region, and we want to determine the value of C. The graph, and then we want to graph this probability density. So in order to graph the probability density, we're going to need to square this function, okay? But to start out with, to calculate the probabilities, we're going to have to start by normalizing this wave function, okay? And normalizing the wave function always looks like, like this. So to normalize a wave function, we know that 1 is equal to the integral of negative infinity to infinity of the wave function squared dx, okay? So this is the normalization condition. In this case, at negative infinity to 0, you don't get anything, right? Your integral should give you 0, so you can start at 0. And then after L, you don't get anything, so we can integrate to L. And the wave function is going to give you C, well, you can say C 1 minus x over L squared dx. So now we're just doing some algebra. So 0 to L, C squared, 1 minus 2x over L plus x squared over L squared dx. All right, and then we can integrate this, so we end up with c squared gets pulled out. We have x minus x squared over L, because 2x is 1/2 x squared, plus x cubed over 3L squared from 0 to L. And then we can say c squared is equal to, let's say we plug in L, so L minus L squared over L plus L cubed over 3L. And we can start canceling things, so this should cancel, this should cancel. That gives us, when we add up these fractions, we have 1 minus 1 plus 1/3 L. So you get c squared L over 3. If we want to solve, remember this is equal to 1, so if we want to solve for c, then c is going to be equal to square root of 3 over L, where we know that L is 1 nanometer, but we're just going to leave it written as L. So that's the normalization condition, and we always have to start with that. But the next thing we want to do is calculate the probability, calculate the probability of finding the particle in a region of width delta x equals 0.01 nanometers at positions 0.05 nanometers, 5 nanometers, and x equals 0.95 nanometers. Now, before you do this, you might want to look at what the graph will be. So remember, when you square this, this becomes a polynomial, and that polynomial should start at, so remember, if you plug in 1 nanometer, that should give us c squared, so that should be 3 over 1 nanometer. So that's going to give us something up here. We should start here, and then this should go down to the same, but now it's a polynomial. Well, it's not a very good drawing. So here's our polynomial. This is going to be 3. This is your probability density with units of nanometers inverse. This is still going to be L, or 1 nanometer. This is your x in nanometers. This is 0. And this function should be this, 3 over L 1 minus x over L squared. That's this function. So it should look like a polynomial. So in order to find the probabilities, we want to find at x1, which would be somewhere over here. Then we want to find at x2, which would be somewhere halfway, and then at x3, which is almost near the end. So we're looking basically for these 3 values. And remember, the probability is best found by p of x delta x. So if we want to find the probability that you're in 0.01 at 0.05, that should be equal to 3 over L 1 minus 0.5 over L squared times 0.01. And when you plug in all these values, this should give you something that's 0.027 or 2.7%. So your probability of finding here should be 2.7%. So we can repeat this for the probability that we're in 0.1 at 5, so probability in 0.01 at 0.5, and that's going to give you, oh sorry, that should have been a 0.5. That's going to give you 3 over L, 1 minus 0.5 over L squared times 0.01. So that's going to give you a smaller percentage, right? That should give you something like 0.0075 or 0.75%, so that's smaller than 2.7. And then the probability, and you're in 0.01 at 0.95. You just plug in 0.95, so that's P of 0.95 times 0.01, and that should give you 0.00008 or 0.008%. So when you look at these, they should make sense with your graph. We were expecting the highest probability here, and that's our 2.7. We expect at half for it to be smaller, and then we expect at 95% for it to be small s, and that's what we find here. Wave function thing, and here we have this wave function which says that, let's say we want to plot it, we have, 2 pi x over L, and we can see that we're 0 until here, and then we have some sort of sinusoidal wave function that goes to L, and then it's 0 again. So this is L. So we have something that looks like this for our wave function, and that's x. So if we want to figure out the probability that the electrons in the interval here, we have to first start by normalizing this wave function. And that's what we always have to start with. So for A, normalizing the wave function means we're going to square this wave function, and we're going to set the integral over the entire function to equal 1. So 1 is equal to negative infinity to infinity of the absolute value of the wave function squared dx. This is the normalization condition that we always start with. Okay? So when we do this, we can see if you integrate from negative infinity to 0, you get 0. So we can start at 0. From 0 to L, you get something non-zero, and then from L to infinity, you're going to have 0 again. So this is going to be c squared sine squared 2 pi x over L, and then dx. Now, obviously, we're going to need some sort of substitution here. We'll use a u substitution, but I'm going to call it theta just for simplicity. So we'll say theta is equal to 2 pi x over L. That means d theta is equal to 2 pi over L dx. And that means we can change our limits of integration. So where x equals 0, that's going to become theta equal to 0, and where x equals L, that's going to become theta is equal to 2 pi. All right, so this is standard use substitution stuff. So that's going to mean that when we pull this stuff out, you end up with c squared L over 2 pi from 0 to 2 pi. That's our changed limits. Sine squared theta d theta. Okay, where we just substituted this dx in here, and that's how we got this and this. Okay. All right. So we aren't going to go, this isn't a math class, so we're going to use this, this feature saying that we know when we get this function, we know what the answer is. So we're going to pull that out, and we're going to get c squared L over 2 pi theta over 2 minus sine 2 theta over 4 from 0 to 2 pi. Okay, and when you plug all this stuff in, you end up with c squared L over 2, which means that c, because this is equal to 1, c is going to be equal to square root of 2 over L. And so that is our normalization condition. All right. So that's part A. Then if we want to calculate the probability, that's going to be the integral from 0 to L over 3, right, over the range 0 to L over 3, which should be pretty much to like here-ish, of the same function. So in this case, since we know what c squared is, we'll end up with 2 over L sine squared 2 pi x over L dx. Now this is essentially the same integral. We're just pulling out this 2 over L, and then we do the same trig substitution, not trig substitution, u substitution. So you have L over 2 pi, 0 to 2 pi. Well, in this case, the only thing that's different is it's not 2 pi. So when you do the u substitution, you go x equals L over 3 becomes theta. Because of our u substitution, we plug in L over 3 and we get two pi over 3. So we go from 0 to 2 pi over 3 sine squared theta d theta. Okay? We can cancel some stuff. So we end up with 1 over pi theta over 2 minus sine 2 theta over 4 from 0 to 2 pi over 3. And when you plug in the values, this is going to give you 0.402 or 40.2%. So the likelihood of finding something in this region is about 40%. Okay. Question, and we want to know the value of constant A, which would be this thing right here. Okay, so please take a minute and think about this and then choose your answer. Okay, so think about this. We always want to, and this is nice because they gave us the probability density, not just the wave function, but we know that the normalization condition is 1, negative infinity, p of x dx, where p of x is the wave function squared. Okay, in this case, we can see that we're integrating from 0 to 2 of this triangle. But the main thing we need to realize here is what an integral is the area under this curve. So if we find the area under this curve, then we just set that equal to 1 and we solve to get A. So remember, it's a triangle, so 1, that's the normalization condition here, is going to be equal to 1/2 base times height. So 2 millimeters, because the units are going to matter, times A. All right, so you can see right away that the 2's cancel, and we get 1 millimeter divided by, sorry, we get A times, well, okay, let's just do it. 1 over 1 millimeter equals A. So A is going to be 1.0 millimeters inverse, and that's going to give us answer B. Okay.